We're looking at motion of charged particles. We've done motion of uncharged particles, we've done motion of cars and wizards and hobbits and tennis balls, and now we're looking at tiny little particles that you can't see, but they do in fact, for the most part, follow all the same rules we used before. They have a different, because of the charge, there's sort of a whole new piece. There's a new source of acceleration, right? Which is electric force. But really, it's all the same stuff. And we use the same methods to find speeds or velocities, or if it's acceleration, then you have to use this one down here. But the first little bit we're looking at, like the first part of our video will be conservation of energy. That's the first video and all the examples. And the second part will be using net force. Okay, so if we're looking at conservation of energy, it doesn't change, right? It's still ET1 and ET2. And listing the energies, there's no springs involved, so I didn't bother listing spring energy, and we don't consider friction, so I didn't bother listing friction over here. We're just looking at, the basic, mechanical energy of kinetic and gravitational plus electric energy. In fact, we neglect gravitational in everything that we do. So when it comes down to this unit, dealing with electrical charged particles and everything we do, you end up with this formula here. But we actually simplify it even more by saying that, get all the EKs on one side and all the EEs. And, what it means is the sign is opposite. It's like the gain or the amount of kinetic energy that the particle loses will be equal to the amount of electric energy it gains, or vice versa. And so, really, then the change in is the same, the magnitude of the change. The second thing I'm going to do is, so you keep that in mind, and then the change in electrical energy is actually Q change in V. And we learned that formula earlier. So this actually leads to a nice formula that we can apply. Okay? So this becomes a very important formula. We're thinking in terms of magnitude, so sign doesn't matter very much. And I'll show you how to apply that. Okay, in this first example then, we have an alpha particle, which I believe is a helium, the nucleus of a helium. So it's a helium particle, a helium atom with no electrons. So then it would have a charge of 2, positive 2. And we know its mass. And we're saying this particle is sitting in a parallel plate apparatus. It's at rest at one side, and it's allowed to accelerate across to the other side. Okay, and what speed does it get there? How fast is it going when it gets there? Okay, under two different conditions. So here's the information we know. We know V1 is 0. We know the charge, we know the mass, and at least for part A, we know the voltage. Potential difference. So there's our equation. Okay, whenever you're dealing, if you're looking for speed, velocity is a bit erroneous because it should be speed, but if you're looking for speed and you're given volts, this is probably the formula you're going to use. Okay, just subbing in 1/2 is just that, mass is that, V2 is what I'm looking for, this is all 0, Q and V, rearranging, solve for V2. And as I say, a good answer, like that's a big number, 440,000 meters per second, but that's typical. That's a good answer. A bad answer would be one that I'd be concerned for sure if it's greater than 3 times 10 to the 8. Sometimes they're smaller than 10 to the 5, but never greater than that, obviously, because then I either wrote a bad question or you screwed up. Okay. Okay. In part B, right? In part B, I didn't bother doing the solution. But if only traveling through half the plate separation, it's really only traveling through half the potential difference. So it's the exact same question, exact same solution, but change in V is 1,000. And I would say you could try it yourself. Try put it in your calculator, see if you get the right answer. The right answer is not half, by the way, right? It's not half because this might be a half over here, but you're still looking for a square root, right? So it's not half, but it is smaller, and that would make sense that it'd be smaller because it's going through half the potential difference. Okay, example 2. All right, little pith ball of mass, very tiny, has a positive charge, very tiny, It's slowly pulled at a constant speed by a string, a distance of 50 centimeters through a potential difference of 800 volts. So let's just, like a picture helps a lot here. It's then released and allowed to fall back to its original position. So let's just see. So it was sitting here where it had a positive charge. It was sitting here. Like you're saying, well, how do you know this is a negatively charged thing? Well, I know that because if you had to add work to pull it away, it must have been being pulled away from something negative. That's implied in the question. It never says it's being pulled away from anything negative. But if I had to, if I had to work to pull it somewhere and it's through a potential difference, it means that I was working against an electrical force. Anyway, so my picture here says this is the start and the finish position. But, partway between start and finish, it got pulled away to here, pulled half a meter away and through that potential difference. So 3 parts: work done by the string and moving the pith ball, which is obviously done by the person pulling the pith ball. Calculate the magnitude of the average force required to do that work. And what I'm hoping to show you here is that the old formulas will still apply. And then kinetic energy when it arrives back, and the speed when it gets back. Okay, so it's getting pulled away, doing a certain amount of work, and we want to find that work. We want to find out how much force was applied to pull it away, and then we want to find out how much energy, like when it's released back, the amount of energy and speed it's got when it hits the whatever this is. Okay, so to find work is just Q change in V, so that's easy. Hard to put a check mark. I don't know what a good number is. In this case, so far that's the only information we know. But that's how you do it. Charge times change in voltage. Part B is force. Well, the old methods still apply. Work equals force times distance. So to find the force, you just divide by the 0.5 meters. Okay. Part C, well, to find the kinetic energy when it gets back, the work you're applying is equal to the change in energy. That's all it is, right? So that's the work energy theorem. So work is equal to change in energy. So the kinetic energy when it turns will be that where it started, or the work you did to pull it away. It'll be exactly equal to the kinetic energy it has. And to find V3, then you just apply. Old methods still work, right? 1/2 mv squared. This time a small number, well, 8 meters per second, a relatively small number. But I can check mark it because, this is a pith ball we're talking about. It's not some subatomic particle traveling near the speed of light or something like that, right? This is a pith ball. You've actually done this. You pulled it away, let it go, it flies back. It goes pretty fast, 8 meters per second, but it's not, super fast. Okay, moving on. Example 3. Oh, I love this question. 2 electrons are held that distance apart, and then they're released. With what speed are they each moving when they are a large distance apart? And large is a funny word, right? What does that mean, right? We know there's an R here. What's this R, right? So if you look at the situation, you say R1, they're very tiny, very close together. Obviously, this is exaggerated. Initially, they're close together, but obviously they're gonna want to move apart. They're both negatively charged, right? And that's really close. They really want to take off. And then when they're a large distance apart, when they're infinity apart, we're looking for how fast they're going. Okay, so just looking at my data, well, they're electrons, so I know their charge. I know their masses because they're electrons. I know their initial speeds, A and B are the 2 electrons, and I'm looking for their final speeds. They'll be the same thing. There's no reason for them to be different. But, just looking at what's going on, my energy transformation, I start with electrical energy. It becomes kinetic at the end, right? So when they're infinity apart, we can assume there's no electrical energy between them anymore. That's basically the idea, okay? So large distance, you have to assume that at that point there's no electrical. So all you're saying is, because we know change in E equals change in EK, change in EE equals change in EK, right? So it starts with electrical energy, That's all there is at the beginning, is this electrical energy between them. It equals to the sum of their kinetic energies. Each particle, each electron has its own kinetic energy, right? So just going through the solution, made a few notes here. I just simplified it by saying they're the same charge. There's Q, QA, Q, whatever. And we know their V's are the same. So really the equation simplifies, solve for VA. And it is a very big number, but like I said, those are typical numbers, right? And it should be, it's less than 10 to the 8. That's my big flag that everything's okay. All right, so obviously I went quick through that, take time and write it all down, but I'm moving on. Okay, last example, potential difference required. So we're looking for V to accelerate. I can't remember what that is, if that's a deuterium, if that's maybe an isotope of hydrogen. With that mass and that charge, yep, must be of hydrogen because it's only got one positive charge. Maybe that's I think it's a hydrogen nucleus with 2 neutrons is what it is. But anyways, it's going from rust, V1 is 0, it's got a V2, and we're looking for change in V. So this is just a simple application again of this formula. You can just see, I'm going to do this fairly quickly here. You can pause it if you want to write it all down, but just applying the formula, isolating change in V, and it's 260,000 volts, which is significant. That's a lot of volts, okay? But there's not many coulombs that are moving, in fact, very few. So the total amount of energy would be really small, right? Because the number of coulombs is times 10 to the negative 19. So actually the amount of joules would be really tiny if we figured it out. Anyway, that's it. That's part A. Part B is coming right at you.